So in the previous video, we started talking about the complex exponential, and we postulated certain properties that we want the complex exponential to satisfy as a generalization of what we are familiar with for the case of the real exponential. And from there on, we were able to come up with an expression for the Euler's formula, which is e to the power of I, and it's generally written in terms of the variable theta, is cosine theta plus I sine theta. Now, one of the very useful uses of the Euler's formula is actually to represent complex numbers in its polar form or in vector form. So just recall that we've talked about previously that in the complex plane, where this is the real axis, and we can label this as x, and the imaginary axis we can label it as y. A point z, which is x plus iy, can be represented as a two-dimensional vector, where this is x units and this is y units, or iy units, and this is the complex number z. And of course, in terms, now this sort of vector has a magnitude, which we call modulus of z, or r, and then it makes an angle theta with respect to the x-axis. And typically, we've been denoting the vector z in polar form as modulus of z making an angle theta with the x-axis, or r making an angle theta with the x-axis. Now, with the Euler's formula, we can actually we can get rid of this sort of cumbersome notation and actually make use of the Euler's formula to represent the complex number z in its polar form. And the way that works is, if this is a vector of magnitude r, then its component along the x-axis is r cosine theta, if theta is the angle that this vector makes with the x-axis, and its component along the y direction is r sine theta. So to arrive at the point z, we can move x cosine theta along the x-axis, or sorry, r cosine theta along the x-axis, right? And then we make a 90-degree rotation to move along the y-axis, which a 90-degree rotation in the complex plane is given by the unit imaginary number, because if you recall, like if you label points along the x-axis, then if you have 1 unit along the x-axis here, then 1 unit along the imaginary axis is labeled by the symbol I. And in fact, I is essentially a 90-degree rotation, because multiplying a complex number I by I is essentially multiplying it by a complex number whose magnitude is 1, making an angle of 90 degrees, so it induces a 90-degree rotation. So we can think of a way to arrive at the point z as moving r cosine theta along the x-axis, and then turning ourselves by 90 degree, so multiply by I, and then move unit r sine theta along the y-axis. So this is another way to write the complex number z in terms of its polar representation, which is in terms of its magnitude and the angle that it makes. But notice now that this is r cosine theta plus I sine theta, and cosine theta plus I sine theta is actually nothing but e to the power of I theta. So this is r e to the power I theta. And so the complex number at z, whose magnitude is r, and which makes an angle theta with the x-axis in the counterclockwise direction, can be represented in a form where z is r e to the power of I theta, and this is sometimes called the polar representation of the complex number. Z, right? And this makes it very evident when we again talk about, let's say, multiplication of complex numbers. So let's say we have two complex numbers, z1, which is r1 e to the power of I theta 1, and z2, which is r2 e to the power of I theta 2. Then their product, say z, which is z1 times z2, is the product of these two, which is r1 r2 e to the power of I theta 1 e to the power of I theta 2. Now recall the property of the complex exponential, that the product of exponentials I theta 1 and I theta 2 can be combined to be written as r1 r2 e to the power. We can actually add the arguments and write a common exponential. So I theta 1 plus I theta 2. And now we see that multiplication of two complex numbers. Essentially what it does is it magnifies the magnitude. Let's say we're thinking of this as z1 multiplying z2. Then what's happening here is that the magnitude of z2, which is r2, is getting amplified by a factor r1. If z2 was making an angle theta 2 with the x-axis, then the new vector now makes an angle theta 1 plus theta 2 with the x-axis. So there's a rotation by an amount theta 1 and a magnification by a factor of r1. So this is a very useful formula especially to represent complex numbers in their polar form. So yeah, I hope this was a useful introduction to the Euler's formula and polar representation of complex numbers. And let's talk more about the Euler's formula and see some of its uses in the next part of the videos. I'll see you there.